The number and types of crafts built to let man fly seem at times uncountable. Blame it on the unquenchable thirst to fly. For if a design can be imagined, someone will build it. And no matter how impossible it seems, attempt to use it for flight. Nowhere, though, do the forces of nature stand in such complete opposition to man's will than in the unusual challenge of vertical flight. When you strip flight down to its most basic elements, you inescapably come to a passion for agility. To fly and not to surrender to the forces of nature at all is both preposterous and surprisingly attainable. To do so, one wires a human being into a lifting system that is as light as materials will allow and as powerful as engine manufacturers can make it. Sikorsky opened the door to vertical flight with the helicopter. The secret was to look at the large main rotors as wings. Rotating wings, of course, but wings. If you did that, you suddenly saw what Sikorsky saw: lift and power. After that, it was a matter of controlling the wing's angle of attack and providing a steady supply of fuel to a large engine. Here, he sets a world record for hover over a single spot. What followed Sikorsky in the vertical flight community was wave after wave of new ideas and experimental designs. Many inventors saw their labors of love tested by the Army Air Corps. However, most would not pass the prototype stage. At the same time that one engineer was tinkering with rocket packs, others were working on what are called tilt-rotor aircraft. In fact, there were several initiatives, all driven by enormous leaps in engine technology and helicopter rotor design. Tilt-rotor aircraft differ from helicopters in one important respect. They get their lift both from their oversized blades, called prop rotors, and from their wings. Transitioning from vertical or near vertical flight to horizontal flight moves lift from the rotors to the wings. Therein lay the weak link. The stresses on the airframe during the transition are horrendous. Early tilt rotors often failed during this phase of flight. Notice the use of thrust vectoring in some early designs. One of the most promising applications of tilt-rotor design is the Bell-Boeing V-22 Osprey, a direct descendant of the Bell XV-3, the VTOL V-76, and the XV-15. The V-22 uses a pair of 6,150 horsepower turboprops, mounted with prop rotors 38 feet in diameter. Sadly, even today's advanced engineering hasn't prevented it from suffering to the same structural failures that plagued the entire design family. By 1992, 2 of the 4 prototypes had already crashed, and all but the Marines had lost interest. More promising in the line of vertical flight designs were the tail sitters, the Convair XFY-1 Pogo, the Lockheed XFD-1, and the Ryan Vertijet. The idea behind all 3 was the same. The pilot would engage the engine and essentially pop up into flight. The mission was to protect a field full of long-range bombers from attack until they could get off the ground. Their vertical orientations meant they could do this without the use of a runway, which meant they could be deployed just about anywhere in the world. Not to be confused with the tilt-rotor aircraft, their engines merely pulled them to altitude where they transitioned to vertical flight and used their wings for lift. The tail-sitters, though, had 2 fatal flaws. They spent most of their useful loads just getting into the fight, and the pilots disliked looking over their shoulders to land. Despite the problems with designs, the idea of vertical flight is rooted in some compelling issues of practicality. These soft field landing and takeoff tests bears witness. Runways are the Achilles heel of fixed-wing aircraft. Without them, you crash. But unless they are paved and fixed, you are at the mercy of Mother Nature. And in war, that just isn't acceptable. The vertical flight fleet overcomes this limitation, allowing aircraft to take off and land without regard to field conditions, to move forward with the battlefield, no matter what the weather. One of the first true vertical takeoff and landing aircraft was the Harrier, and the Marines were quick to buy it. Early testing at NASA Ames Research Labs firmed its flight envelope. Marine acceptance followed in 1968, with the AV-8B model entering the fleet in 1983. With 4 main vectored thrust nozzles and puffer jets in the nose, on the wingtips, and in the tail, the pilot can take off and land without any runway roll, and then turn the Harrier in almost any direction, using almost any combination of yaw, pitch, or roll. Unlike its fixed-wing brothers, the Harrier can adjust its takeoff or landing roll to accommodate whatever runway length it has, and that is its secret. By adding more or less nozzle deflection to its airspeed, it can increase or decrease the takeoff roll it needs. The more nozzle, for instance, the less runway length needed. Along with the Harrier, the out-and-out winner in the vertical flight business is the helicopter. Although they first flew about the same time as the Wright brothers, helicopters played no role in World War II, and even up to Vietnam were primarily unarmed platforms. Helicopters were transports and heavy lifters. Most recognized of the early models is the Flying Banana, the H-21 workhorse. Notice the collapse of the right strut during early tests of its novel flotation skids. The big 7-bladed Super Stallion is perhaps the all-time heavy lifter for the United States. The CH-53's 79-foot rotors are powered by three 4,000 horsepower jet engines. It can lift 32,000 pounds, 16 tons. Lifting and transporting artillery, cargo, and troops is a job well suited to the helos. Some words of caution, though, are in order. For instance, what is the procedure should an engine fail? Lower the load if there is power. Drop the load if there is not. The heavy lift capabilities of helicopters have commonly been put to use in a rather ironic role, recovering downed helicopters. Another heavy lifter is the S-64 Sky Crane. Notice the drag chute behind the H-3. This keeps the load centered along the flight path of the Sky Crane. The Boeing Vertol Chinook and its cousin, the Sea Knight, are the workhorse helicopters for the services. The twin rotors are mounted above the main fuselage, leaving the internal cabin area unobstructed for carrying artillery, troops, and small vehicles. An interesting use of the helo was the air recovery of cruise missiles. Here, the rigging is used to snag the cruise missile while it descends. The results were not always the success engineers envisioned. Perhaps no helicopter is as well known as the UH-1 Huey. Introduced in the 1950s, the Huey has been modified and upgraded for 4 decades. Now enlarged to seat 2 crew and 12 to 14 troops, the Huey has a 1,900 horsepower engine and a service ceiling of 12,500 feet. The military's need for armed helicopters was fanned by the Vietnam War. Hueys were modified with rocket pods and door-mounted guns, but the need was for something more, a dedicated gunship. Bell had an ingenious solution. Strip the Huey of its bulk and engineer around the proven engine. The result is the Cobra, a powerful gunship that flies escort for the Sea-Night troop transports, as well as dedicated combat sorties. Its armament includes 8 tow missiles or Hellfire rockets, 2 rocket pods, and a 20mm cannon in its chin turret. A true symbiotic beast. The weapon's fire control systems are slave to the pilot's helmet. Similar in profile to the Cobra is the McDonnell Douglas Apache helicopter. Winner of the formal competition for an Army gunship, the Apache is a lethal weapons platform, supporting on its wing mounts anything from AIM-9 Sidewinders to Hellfire missiles. Like the Cobra, the Apache surrounds its pilot and gunner with a bathtub of armor and is intended to take punishing hits over the battlefield without suffering a failure of any critical system. Of particular concern was protection from armor-penetrating shells used by the Warsaw countries. They were designed to explode inside the cockpit. As in any aircraft design, engineers sift through a basket of trade-offs when designing a helicopter. Weight and airspeed, weapons configurations, and pilot workload. Everything is tested, and each is a slight trade-off, one for the other. Needless to say, helicopters are powerful, but they are fragile. Runaway centrifugal forces are deadly to a helo, as are rotor strikes, mast strikes, and plowing the chin into the ground. Icing is as much a problem for rotor blades as it is for fixed-wing surfaces. This icing rig loads the rotor blades while high-speed photography monitors both accumulation and shedding. Missiles are potent weapons on the battlefield. Most, carried by soldiers or by helo drivers, use IR, or infrared sensing heads, and home in on heat sources for the kill. In developing a battlefield missile, fuse testing is undertaken on a sled track with dramatic results. These are then followed by live fire tests against target fixed-wing drones and drone helicopters. The threat of the shoulder-launched missile is sometimes discounted by air-to-ground aircraft and helos. All too often, pilots believe they can outjink their adversary. As this video dramatically demonstrates, keeping the crosshairs on target is almost easy. When you consider the agility of the helicopter and its ability to continuously hover, you might conclude that it and the Harrier make spectacular weapons platforms, which is in fact true. Those pilots that enter the world of vertical flight face a challenge that combines a delicate touch with a deadly array of firepower brought to bear right on the battlefield itself. For those few, it is a challenge of lethal weapons and aerodynamics unlike any in the world.